We're going to add in another test today. Before we add in that other test, I want to do a recap of what we know thus far, because it has been a weekend. Alright, so I need this side conversation. Stop talking to each other. Hush. Yes, I am reviewing because we are getting to the point, and I could tell on Friday that some of your brains are getting saturated with all of these tests. We have to know some of these tests, or at least have a functioning knowledge of some of these tests for us to use this fifth test. So I need to do a quick review of all of these things, and we'll go from there. Don't worry, I won't put you on the spot when you tell me, but what are some of the tests that we've done? Let's start in order as we're going through. We'll start with our Nth Term Test. We did, but Nth Term is usually what I will start with when I test things. Nth Term Test. Nth Term Test said if I have the summation A sub n, I'm just going to start them at 1 for today. And I take the limit of the inside sequence. What do I want it to not equal? 0. If it does not equal 0, therefore you can tell me that series diverges. Can't tell me anything else. That's the only condition you have to worry about. That one. Cool? Alright, then I'm sort of working backwards. What's the first one we did? Geometric. That one's going to become pretty important today. There's 2 of them that'll be very important today. First one is my geometric. A geometric series had a very certain layout, and I'm going to keep repeating it. It was a constant, it was a number raised to a variable exponent. And in our case, the constant we looked at, we called it r for the ratio, because it's multiplying by something each time, raised to the n exponent. Again, I keep saying this, but is everyone clear on how this is a number raised to a variable exponent, right? Our conditions for this one, all we had to do was look at r. If the absolute value of r was less than 1, what could you tell me about the series? It converges. If the absolute value of r was greater than 1, if the number I'm looking at is like 5/3, 6, 7, it's going to diverge.
If it's 1, it diverges.
If it's 1 raised to the n, that is 1 to the 1, which is 1, 1 squared, which is 1, 1 cubed, which is 1. So it's just adding 1 plus 1 plus 1 plus 1 plus 1 plus 1. So it's getting bigger, bigger, bigger. It diverges. Cool? You bring up a good point, Aiden. When you're doing these, some of them you should be able to look at and just like plug in numbers and see what happens. Like, for example, I talked about it on Friday, something like n squared. N squared is 1 plus 4 plus 9 plus 16. That just keeps adding bigger and bigger numbers. Is that going to converge or diverge? Diverge. So you should be able to look at some of those and be like, yeah, that one definitely does that. And then Friday we added 2 new ones. The new one we added at the beginning was our integral test. And hopefully those of you that were out had a chance to check it out on the video. Integral test. Integral test had some conditions to it. And I'll come to some of you for these. Let's start with you, Claire. Claire, what was one of my conditions for me to be able to actually try the integral test?
Hold on, let me look at my very damp notebook. 1 second.
We'll phone someone else. Norvik, what's one of them?
Positive.
It has to be positive. Livia, do you remember any of the other ones? It has to be continuous. And then I believe, is that Allison that you sang it back there?
No, it was Jacob.
It has to be non-increasing. Because both of you were so very confident, and it was very not one of your voices. Yeah. So it has to be those three things. If it's not those three things, I can't use my integral test. Dude, you can't even look at it. You can't even sniff at it. The integral test said, if those three things are true, then the improper integral from 1 to infinity of a sub n dn and the summation from 1 to infinity of a sub n, that the series and the integral are going to do what?
Converge or diverge together.
Right, they're going to do the same thing.
That was me.
Yes, thank you. And right, the reason I was doing this is because I can deal with integrals. I can't deal with infinite sums. Some of those ones I could not deal with, so I took it out of sum world. I looked at the area underneath the curve, and we talked about how it's like sort of like the Riemann sum. And it makes sense that if the Riemann sum converges, that the series would also converge. The last one we looked at was an outgrowth of our integral test. And this is also another one that's going to be very useful today. What was the last one we talked about? The P-series test. P-series test had a very specific layout from 1 to infinity of 1 over the variable raised to a number. It was always 1 over the variable raised to the number. And I made the comment that this is sort of like the ugly cousin to my geometric, because the geometric is a number raised to a variable. This is 1 over a variable raised to a number. So they're sort of opposites of each other. Jacob avoids slapping Leo. And there were some conditions on this. If P was greater than 1, what happened to that series? It converged. If P was between 0, 1, or if it was equal to 1. So if I just had the series 1 over n, we started by looking at that one. So 1/2 plus 1/3 plus 1/4, continuing on. These diverged. So today, in our new test, this one will be very useful, and our geometric will be very useful. Because today is so involved with previous tests, take about 5 minutes. I want you to quiz people around you back and forth about the 4 tests we have thus far. Talk about the layout of them, talk about the conditions. Once you are done, do it again for about 5 minutes so you absolutely know these 4 tests. This new test is going to be called a direct comparison test. The new test we're looking at, direct comparison test. There's also something called a limit comparison test. It used to be in the curriculum, but the AP test took it off, so we're not talking about that one. Limit comparison test takes the limit of 2 functions on top of each other, and based off of that you can tell if it converges or diverges. But because it's not on the AP test, We're going to save it, and if we have time, we'll loop back to it at the end after we take our test. The direct comparison test says two very specific conditions. I'm looking at two summations. A sub n and B sub n. And we're going to hopefully compare these two. First off, I want A sub n and B sub n to be greater than or equal to 0. I don't want them to be negative, because if they turn negative, life goes crazy. So that's really my one big condition. Just like with the integral test, I want it to be positive, continuous, and non-increasing. This one, I just want them to be positive. I want them to be greater than 0. So, that's an and. Yeah. I'm not saying adding them has to, well, it would be the same. Not necessarily. So, the conditions I have, how did I write it last period? Because I really like to have it. Well, I write it in specific ways, and sometimes it makes sense. The first one, if the summation from n equals 1 to infinity of B sub n converges, and A sub n is less than or equal to B sub n. In other words, if I have a function that is converging and I look at a smaller function, that smaller function is going to converge as well. Let me translate that how I just said it in human speak. If a bigger function, or bigger series, I should say, if a bigger series converges, that means any smaller series than it also converge. So if I'm looking at two series and a bigger series converges and I have something smaller than it, that means that smaller one will also converge.
What do you mean as the smaller? Like the smaller coefficient?
The numbers, when I plug them in, one number is smaller. So like if I plugged in n equals 1 to both of them, and one of them got like 1/3 and one of them got 1/5, 1/5 would be smaller than it, and I'll go from there. You'll see when we're looking at some examples what I mean by smaller. Cool? The only other case for this is the exact opposite. If I'm looking at A sub n now, and A sub n diverges, and still A sub n is less than B sub n. So I'm looking at the opposite case of this. Now I have a smaller series that diverges. If I have a smaller series that diverges, that means the bigger series is going to diverge. Again, one more time, translation. If a smaller series diverges, any bigger series will also diverge. Oh yeah, Bn, sorry. Thank you. Now, these are the only conditions you can use. Don't try doing anything else with this. I am not saying that if a smaller series converges, the bigger series converges. That's not true. The only thing there is if a smaller series diverges, something bigger than it will diverge. It's also not saying that if a bigger series diverges, that the thing smaller than it will diverge. The only two cases in which this works are these two cases. Take another 45 seconds. Explain in your own words to someone around you what you think these mean at this point. 3, 2, 1. Example number 1. Dang it, I did this first period as well. I'll start drawing my E's as summations. Example number 1. Let's look at the summation. Starting at, well, let's start at 2 just for shiggles. One over n squared plus 5. Alright, nth term test. I plug in plug in infinity in there. 1 over infinity gets me 0. It doesn't tell me anything. I can't use it. So, it's not geometric. It's not a number raised to a variable exponent. I could maybe integrate this using an arctangent and using the square root of 5 squared, but nope, I don't want to do that. Is it a power series?
Oh, is that what P series
Well,
means?
no. It is a power series.
Right, remember a power series.
P series?
P series, yeah, sorry. It does stand for power series. I'm not going to use the word power series because coming up in a little bit, we're going to run into something else that we're actually going to call power series. Remember, a power series was 1 over n. Dang it, P series. A P series was 1 over n raised to a power. Is this a P series?
No, it's not reasonable. Well, it could be reasonable.
Yeah, so give me a second. I have 1 over n to the second power. I have a power in there. It sort of looks like a P series. What is preventing it right now? The plus 5. So I'm thinking this sort of looks like this series. It sort of looks like 1 over n squared, which is just 1 over n all squared. Because it doesn't matter where I put the squared. 1 squared is 1. It's always going to stay at 1. So I could write it as 1 over n squared, or I could write it as 1 over n parentheses squared. This series, you already told me it's a P series. And in this case, is it a converging P series or diverging P series? P is greater than 1, so it's going to converge. Alright, so I just found a really easy test that pretty much looks like what I'm looking at. It's really close to. So let me compare the two. Right now, I have 1 over n squared plus 5. And I have 1 over n squared. Now, if you can't rationalize in your head with these fractions, don't try it. Literally just plug in a number. If I plug 1 into this is going to be 1 over 1 squared plus 5, which will be 1/6. This will be 1 over 1 squared, which is 1. I'm just taking any number I want to. Which one is bigger, the left side or the right side? The right side is bigger. I'm only plugging a number in there so I can see which one is bigger. You shouldn't need to plug a number in there. You should be able to look at this and say the denominator is bigger over here, therefore this one will be smaller, and go through there. But if that is tripping you up, take any number you want, plug it in there, and you can see which one is bigger. So in this case, I have this thing, which I know converges. It is bigger than the thing I'm looking at. Therefore, what could you say about the smaller thing? It also converges. That is the direct comparison test. Yes, ma'am? This, I said the front half of this looks like a P series. If only I had ignored that plus 5, it sort of looks like it's wanting to be a P series just without that plus 5. Now, I literally could have chosen anything. That's why this test is so useful. I can choose 1 over n. I can choose 1/3 to the n exponent. I can compare it to literally whatever I want to. But it makes sense that I'm going to compare it to something that it sort of looks like. I'm not going to go off randomly. Let's say, well, let's compare it to n to the 5th power times 5 divided by 4. Like, I'm not going to just choose something random out of my butt. I'm going to look at it and say, great, this is sort of like a p-series, if only I could ignore that plus 5. Yes, sir?
So we have to do, like, the 1 over n squared. Like you just picked that because they kind of...
Because the beginning of it sort of looked like it. It looked like it was going that way.
You don't need the 5 whenever you're looking for that?
Right. I'm going to compare it to something. I don't know this. I'm trying to figure this out. Let me look at something I can easily figure out. Remember I said we're going to use some easy series, and it's usually geometric and p-series. I can pretty much almost all the time say, great, power's less than 1, greater than 1, it's going to converge or diverge. Or the ratio is less than 1, greater than 1, converge or diverge. So let me get it to something that's really easy to say, boom, that one definitely converges. Let me compare it to mine. Ah, this is bigger than it, therefore I know the other one has to also converge. Cool? Correct. I'm just going to pick something that looks similar to it so that I can go about it and compare them pretty easily. Word? So this converges by direct comparison. Yep. What?
Why do you never box it?
Just to make you mad. Yeah.
Aren't you supposed to find the bigger one and then compare it and find if the smaller one is converging?
No. This is what the test is saying. I'm saying because this one is smaller than this one, and I already know that this one converges, I can also say that this one converges. I'm comparing. I'm saying, great, I have something that is bigger. The bigger thing converges. Therefore, the thing I'm looking at, my series, also is going to converge. Cool? It's fitting rule number 1 of this. It's saying a bigger series, the thing I came up with in my head, the 1 over n squared, converged. Therefore, the one I'm looking at, the smaller series, will also converge. Cool? Try this one on your own. It's going to be very similar to the thing we just did. Why don't you try summation n equals 1 to infinity of 1 over, let's go 4 to the n plus 6. Why don't you tell me if that one converges? Does it sort of look like? It sort of looks like a geometric, and I'm saying that because if I look right here, it sort of looks like the summation n equals 1 to infinity 1 over 4 raised to the n. It sort of looks like that, right? That series, 1 over 4 to the n, Daniel, is that going to converge or is it going to diverge?
Converge.
It is absolutely going to converge because the ratio is less than 1, so this one would converge. So now that I have something I know converges or diverges, let me compare it to what I'm looking at. I'm looking at 1 over 4 to the n plus 6. I know 1 over 4 to the n converges. Which one is bigger, right side or left side?
Right.
Right. Okay, I have something bigger that converges. Can I tell anything about the smaller one? Yes, it is also going to converge by direct comparison.
Do we actually have to write out the less than, or can we just write, can we just write?
You're going to want to, like this is the train of logic I want to see.
Okay.
Cool?
Yeah.
Alright? Everyone with it? Let's do one more quick example. Let's look at this one. Alright. 1 over the summation. It's example 2. Jacob. Hi. Now, up until this point, literally any single time I have seen a square root, I've done one thing with it. What have I done? I haven't. Yes, I have sometimes turned it negative, but I've always turned it into an exponent. So really, this is 1 over n to the 1/2 minus 5. Now, I have something, a variable raised to an exponent. What type of series would that sort of be like? P series. And if I ignored that 5, I would think I could maybe compare it to 1 over n to the 1/2 power. That fits my P series. The P is less than 1, therefore it's going to diverge. Great. I know I have something that diverges. I have found something that is somewhat related to my series, and I know it diverges. So let's compare the two. I have 1 over square root n minus 5 and 1 over square root n. Again, some of you should be able to, and really all of you should be able to look at this and say, great, which one's bigger? But if you can't, plug in a number. This side, the denominator is subtracting 5. So this denominator is smaller. Therefore, the overall thing will be bigger. Alright, I have a smaller something that diverges. Does that fit one of the conditions that we put on the front? Yeah, the conditions we put on the front was saying if I have a smaller something that diverged, that means the bigger series also had to diverge. My known right now diverges. The thing that's bigger than it, what am I unknown, means it also has to diverge. The denominator is smaller. When I divide by a smaller denominator, the fraction gets bigger. This diverges by direct comparison.
Can we abbreviate direct comparison?
Yes.
Easy test.
Nee, if you're confused, plug in a 4. See which fraction is bigger. Because I can take the square root of 4. Don't look at me like deer in the headlights. If you're confused, plug in a 4 and do the numbers.
Absolute value of the function?
Wait, so it would be negative contour.
Oh, I made it too big. Yeah. Yeah, change it to like a 1. Change it to a 1. I made something off the top of my head that doesn't actually fit the condition. Okay.
Pause the video.